Hi everyone, my name is Jeremy Binagia, and today I'll be talking about some recent work my group's done studying the effect of azimuthal swirl on swimming dynamics in viscoelastic fluids. There are many situations where microorganisms or individual modal cells like cilia are immersed in a complex fluid environment, and a change in the properties of the fluid can have a profound effect. For example, a change in the mucus surrounding the cilia of the upper respiratory tract of the lungs impacts their ability to pump foreign substances out of the body. Another example is how changes in fluid properties of cervical mucus impacts the motility of spermatozoa, and has shown to be one cause for human infertility. So clearly it is worthwhile to study the behavior of these complex biofluids, that is, their rheology. In both these examples, the fluids the microswimmers are immersed in are laden with large biopolymers. Because of this, these fluids are viscoelastic, meaning they respond both viscously, like a liquid, and elastically, like a solid, to deformation. This is significant since there is now a large body of literature showing that the elasticity of a fluid can substantially impact the motility of microscopic swimmers. When we review the literature on swimming in viscoelastic fluids, by and large, we see that the effect of fluid elasticity is to cause a decrease in the microorganism's swimming speed. On this slide, I've included a list of experimental, theoretical, and numerical studies of swimming in complex fluids that have all found this to be the case under various conditions. My point here isn't to go into detail into this literature, but just to convey the sense that while the effect of fluid rheology on motility is indeed complex, it appears that swimming slower in an elastic fluid tends to be the rule. With this context in mind, it's then very interesting to note that recent experiments for the bacteria E. coli have shown that it actually swims faster the more elastic the surrounding fluid is. This can be seen to the right, where the average swimming speed is plotted as a function of polymer concentration in the surrounding fluid, and here we see a monotonic increase in the swimming speed with increasing polymer concentration. What these researchers hypothesized for the mechanism of this speed enhancement is that elastic hoop stresses, shown in red on the right, created by curved streamlines resulting from the rotation of E. coli's tail and body, decrease the amount the cell wobbles while it is swimming. This decrease in cell wobbling consequently leads to straighter swimming trajectories and thus larger average swimming speeds. After seeing these experiments, we started to wonder, can elastic stresses induce a speed up even for swimmers constrained to swim in a straight line, that is, those that don't wobble? We were motivated by recent work from our group that found that particle sedimentation in a viscoelastic fluid occurs faster if the particle is rotated by an external magnetic field. So we started to wonder if a similar mechanism could be at play for E. coli. Here, azimuthal flow isn't created from rigid body rotation, but rather from E. coli's rotating helical tail and counter-rotating body. To answer this question, we set up our analysis using the Squirmer model, which considers the slip velocity at the surface of the swimmer written in terms of the Legendre polynomials. The slip velocity is meant to capture the swimmer's gait or stroke. For example, it might represent the average motion of a large array of beating cilia on the surface of the swimmer, as is the case of paramecium shown to the right. Very recently, authors have noted the presence of additional terms in the expression which act in the azimuthal direction in spherical coordinates. It is this term that we will make use of in our work. But first, I'd like to discuss the typical case whereby we discard all terms except for the first two polar squirming modes. Using B1 as our characteristic velocity scale, we arrive at the following dimensionless boundary condition. Here, CC is a dimensionless group that is the ratio of the first two polar squirming modes. C denotes the type of swimmer. Here, I've shown streamlines in the co-moving frame of reference for three types of swimmers: neutral, puller, and pusher type swimmers corresponding to C equal to 0, positive, and negative respectively. These values of C and their corresponding names essentially denote how the swimmer generates its thrust. For example, pullers pull fluid around the front of their body, while pushers eject fluid behind themselves to move forward. As I mentioned earlier, we wanted to use the Squirmer model to capture the flow created by E. coli. To do this, we now include one of the azimuthal squirming modes, which gives rise to a new slip velocity. Our new term, highlighted in red, introduces a new dimensionless group zeta, where zeta is the ratio of this new azimuthal mode to the first polar squirming mode B1, and essentially measures the relative extent of azimuthal flow around the swimmer. Well, what does the C2 mode look like? To the right, I have the swimmer in the spherical coordinate system, and now if we look at a plot of the streamlines, in the case of swirl for zeta equal to 5, what we see is that we have streamlines circulating around the top and bottom half of the squirmer in opposite directions. This was the reason we chose this mode, so that we could mimic the azimuthal flow created by E. coli's rotating tail and counter-rotating body. With the model for the swimming microorganism now defined, I'll now describe the equations that govern the motion of the fluid that the organism is immersed in. First, we have conservation of momentum and mass. Here we have the important dimensionless group, the Reynolds number, which is the ratio of inertial to viscous forces in the fluid, which in our case will be much smaller than 1, since we're dealing with microscopic organisms and viscous fluids. On the right-hand side of this equation, we saw the divergence of stress. Well, the stress in a viscoelastic fluid consists of two parts. First, we have a contribution from a Newtonian solvent, and then secondly, we have an extra polymer stress, tau superscript p, coming from deformation of polymer molecules immersed in the fluid. In this equation, we have the dimensionless group beta, the viscosity ratio, which measures the fraction of the fluid that is the Newtonian solvent. And it is the ratio of the solvent viscosity to the total solution viscosity. Finally, to close our set of equations, we must specify a suitable constitutive equation for the extra polymer stress. Here we use the Giesecke's constitutive equation, which models polymer molecules in the fluid as Hookean dumbbells experiencing an anisotropic drag. The first important dimensionless group in this equation is the Weisenberg number, which is a ratio of the fluid relaxation time lambda to the convective time scale. And then secondly, we have the Giesecke's mobility parameter, alpha sub m, which essentially controls the rate of shear thinning in the Giesecke's fluid. Now that we've defined our governing equations and the appropriate boundary conditions, how do we solve this system? What we do is we consider the co-moving frame of reference, which again is the squirmer fixed in uniform flow far away from the swimmer. And in this way, we can use a body-fitted mesh around the particle. Then, we iteratively calculate the swimmer's speed u and rotation rate omega until it is force and torque free at steady state. And we do so by using a highly accurate finite volume solver developed here at Stanford. This now brings me to the results. Shown to the left is the swimming speed u normalized by the speed in a Newtonian fluid, u sub n. That is the speed at Weisenberg equal to 0. This is plotted as a function of the Weisenberg number, which again is measuring the degree of fluid elasticity, and as a function of zeta, measuring the relative extent of azimuthal swirl in the swimmer's gait. What we see from this plot is that for relatively small values of swirl, zeta equal to 0 or 1, we observe a slowdown in the viscoelastic fluid, denoted by u over u sub n less than 1. Conversely, though, things are much different for larger values of zeta, where we observe a speed enhancement in the elastic fluid. While this is shown for the case of a neutral swimmer, we've also explored this phenomena for different types of swimmers. This is shown to the right, where we observe a similar speed enhancement for pushers, pullers, and neutral type swimmers alike at a value of zeta equal to 5. We've also considered different rheological models for the fluid, such as Feeney P, Rodre B, as opposed to the Giesecke's equation that we've used here. Those results can be found in the reference I've listed in the footnote of this slide. To understand the origin of the speed enhancement, we started to look at the stress in the surrounding flow field, specifically the ZZ component of the polymer stress. Shown to the left is this component of the stress in the case of no swirl. Here the swimmer is swimming to the top of the page. What we see is a large elastic wake behind the swimmer. Now if we look to the right, in the case of significant swirl, zeta equal to 5, we see that this elastic wake decreases both in intensity as well as in breadth. What's important to note about this elastic wake is that nominally it hinders forward motion. We can see this by looking at the net force acting in the swimming direction from elastic polymeric stresses. Recall again that the swimmer is moving in the positive z direction. This net elastic force contribution can be further decomposed into two parts. One, normal elastic stresses, and secondly, shear elastic stresses. This is shown at the bottom, here written in terms of the cylindrical coordinates z and rho. And these integrals are taken over the entire surface of the swimmer. So in the plot on this slide, what we're looking at is the integrand to this first integral, which turns out to be the more important of the two elastic contributions to the net force, as you'll see on the next slide. This ranges from theta equal to 0, corresponding to the front of the swimmer, to theta equal to pi, which corresponds to the back of the swimmer. In alignment with what we saw on the previous slide, what we see is that in the case of no swirl, there's a large negative contribution for this quantity. Now, this changes drastically in the case of swirl, where we see this large negative contribution increase substantially, and we'll see on the next slide that this actually leads to the net elastic force actually being positive. By examining all the contributions to the net force acting in the swimming direction, we can provide a full explanation for the speed enhancement seen earlier. This net force, as shown on the bottom of the slide, consists of contributions from pressure, shown in blue, viscous stresses, shown in gold, and polymeric stresses, shown in red. The latter is again further decomposed into normal and shear elastic stresses, as was done on the previous slide. Plotted on the left are these contributions to the net force in the case of no swirl as a function of the Weisenberg number. What we see is that with the introduction of swirl, the latter hardly changes, while the former changes drastically, as shown by the gray area, and actually becomes positive for all Weisenberg number, indicating that it is now propulsive. So taken together, we see from these plots that the reduction in the elastic weight behind the swimmer results in an increase in polymeric thrust on the particle, and we believe that this is the reason for the speed enhancement that is observed. Now up to this point, I've spoken at length about steady swimming, that is swimming in a straight trajectory, but in reality, organisms often change their direction and motion. For example, here you can see a video of E. coli undergoing a characteristic run and tumble motion, whereby it undergoes straight runs interspersed by sudden changes in direction, aka tumbles. Our model that I've described thus far can easily be extended to consider such transient dynamics by allowing the particle director P to be a function of time. To study this in detail, we're going to consider the following change in swimming direction in particular. Looking at this figure starting from the left, we consider a swimmer swimming at a steady speed u, here swimming in the northwest direction. At some point, it begins to execute a tumble, and it will rotate clockwise. After some period of time, tau sub t seconds, it will stop rotating and reach a new steady orientation. We select the angle that the organism sweeps through from this rotation, capital theta, such that it is equal to the mean tumbling angle of E. coli. Numerically, what we have to do now is we're not just solving for u and omega at steady state, but we must do so at each time step. And the way we accomplish this is using a quasi-Newton method, in particular Boyden's method. With this new methodology, we can calculate swimming speeds as a function of time, as I've shown on this slide, with time made dimensionless by the convective time scale A over U sub n. In this plot, the light gray vertical lines mark the beginning and end of a tumble. From this plot, we can see that the swimmer can momentarily experience an increase in its swimming speed depending upon how much swirl is present in its gait, with those with more swirl experiencing a larger temporary gain. This is also observed in experiments. Shown to the right is experimental data provided by Paula Aradier and Alison Patterson for a single E. coli cell swimming in an elastic fluid. In this plot, we too see this sort of temporary speed overshoot. Comparing the speed increase seen in simulations and experiments and under what conditions it might occur is the subject of ongoing work in our group. And with that, I'd like to conclude my talk by highlighting what I think are some of the key takeaways. Here, we found that swimmers that create swirling flow around themselves swim faster in elastic fluids, while those that do not swim slower. And we saw that the cause of the speed up is a reduction in the resistive elastic wake behind the swimmer. Finally, we saw that the speed up can be momentarily enhanced after the swimmer incurs sudden changes in direction. If you'd like more information, feel free to reach out to me. I listed my email at the bottom, or refer to one of our recently published works. Thank you for listening. Bye.